Okay, I'm excited today to introduce Dr. Zhang. He is an assistant professor in electrical and computer engineering department at Utah State University. His primary research focus is in the formal verification of concurrent and probabilistic systems, and he's here today to tell all of us a little bit more about his research and his ongoing work. So there you go.
Well, thanks for the introduction. Today, I'll talk about our work on refutation-based adversarial robustness verification of deep neural networks. So this is a joint work with my PhD student, Joshua Smith. So let me start by emphasizing the importance of formal verification. In our real lives, we have seen accidents and these incidents that are due to failures in our computerized systems, and they often lead to costly and even deadly consequences. So I'll just give a few examples. In 1996, the European Space Agency launched this Ariane 5. Unfortunately, it self-destructed 37 seconds after launch. And the investigation followed showed that it was due to an uncaught overflow exception in the control software. Then as the second example, in 2010, there was a software glitch discovered on Toyota Prius, which causes less than a 1 second lag in the anti-lock brake system. And the result is that 185,000 cars were recalled. Then even a more recent example, in 2018, there was an accident caused by the Uber autonomous driving vehicle, and this accident caused a death of a pedestrian. This was due to the the failure in the perception module on this autonomous vehicle. Basically, it misclassifies the bicycle that the pedestrian had when she was crossing the road. This failure or this misclassification of the pedestrian leaves insufficient time for the vehicle to brake. So for these computerized systems, they have gone through thorough simulation and testing during the design phase. Unfortunately, they're still not enough to prevent these kind of accidents to happen. Just like the famous computer scientist Dijkstra once said, testing can only show the presence of errors, but not their absence. So that's why we need formal verification, where formal verification is basically the application of rigorous and mathematics-based techniques to establish provable correctness guarantees of computerized systems. So the general idea of verification is that we provide some model or a program, and we encode our requirements as one or more, or a set of properties. Then we provide both to the verifier, and the verifier performs this rigorous checking, and if it returns yes, it means that the property is proven to satisfy the model you provide. Otherwise, it will provide a counterexample for the designer to debug the design. So let me just talk about the deep neural networks, and then I'll talk about the deep neural network verification. So deep neural networks basically is a machine learning technique for performing function approximation. Nowadays, it has increased usage in computer vision, data classification, AI-based agents, and many other areas. Modern deep neural networks, or DNNs, have millions of internal parameters that are operated on high dimensional data. So the idea of a DNN is that it transforms the inputs through a series of layers. And through this transformation, it tries to extract high-level abstractions and models of the input data. And the DNN usually outputs a set of labeled data points to approximate a function. So in a way, it establishes the some kind of relation between set of inputs and outputs. So the we have seen a lot of increase in the use of DNNs in safety critical applications, such as the vision perception modules for autonomous vehicles, and airborne collision avoidance system controllers for unmanned aircraft. Now, because the deployment of DNNs in these safety critical applications, we have to make sure that these applications can have guaranteed properties to improve utility and value. So that is why we actually need to do formal verification on these on such DNNs, so that we can provide these kind of correctness guarantees. Also, the formal verification can provide explanations for the actions of neural networks, so that we can better understand the behavior of these complex neural networks. Now, there are many challenges in performing DNN verification. So here I mainly list two of these. The first one is obviously the high dimensionality of the deep neural networks. So basically, let's use ImageNet as an example. It has 224 by 224 by 3, which is this huge number of dimensions that we need to deal with when we need to formally verify in theory, all the possible, inputs in all these possible dimensions, the correctness on all of these. So also, modern neural networks have millions of hyperparameters and operations, and that also, or this fact also makes, formal verification of these DNNs very challenging. The second main challenge is, the lack of formal definitions of safety properties. So, for example, how can we formally specify a pedestrian or a stop sign if we provide, an input image, showing these, these objects? So, because the formal verification engine needs a way or needs a clear, specification on what consists of, or what are considered as, these objects, in order to make, some checking or perform, correctness checking. So that still remains a challenge today. Now, in this talk, we'll focus on, I guess, dealing with high dimensionality, or dealing with the challenges in the high dimensionality of a neural network. So, so let me start by describing what we mean by adversarial robustness. And to understand that, first, let me just describe the adversarial inputs. So I'm using this famous example here. So basically, if we present a picture of a panda to a trained neural network, it might return 57% of confidence, saying the neural network considers it or correctly classify the object in this image as a panda. But if we introduce some noise here, that's the that's what the middle picture represents. So the noise itself is is imperceptible to human eyes, but when we add this noise onto the the picture of a panda, all of a sudden it can fool the neural network into thinking of it as a given with very, very high confidence. So this is what we call adversarial inputs, where we apply small perturbation to the to some input image, which can cause the neural network to misclassify an object or objects in it. Sorry, was there a question? Okay, I guess I can continue. So how can we address this problem in verification? So first, we need to define a local adversarial robustness. Now, if we're given an input X to a neural network, this input is an n-dimensional data. We can consider a network as a function applied to the input. So so we use NN to represent that function. It basically provides a classification, in this case, of this input to provide some output. So the classification is, we use M as its dimension. So a few other things that we need to define local robustness. So let's call alpha the testable point in the input space, where alpha has the same dimension as X, and beta, which is the classification of alpha. So beta is what the network returns. Then we define a region. So a region is basically a high dimensional polytope in the input space. And the region enclosing a test point alpha is defined as this eta alpha, where alpha is basically a point inside a region. So then with these notations, we can formally define a local adversarial robustness. So this says that for all input X in the region enclosing the testable input point alpha, there does not exist an output Y generated by the neural network such that Y is not in the class of beta. In other words, if a neural network is locally robust against adversarial examples, then we can never find an adversarial examples in the region of this eta alpha that can cause misclassification. Okay, so that's what we define as local adversarial robustness. So the contributions of our work, are summarized on this slide. So we first apply the refutation-based abstraction through adversarial input generation. Because again, the high dimensionality problem of the neural network, we have to abstract, the region of an input to the neural network, and then we apply this refutation-based refutation-based techniques to basically find these adversarial examples first. I'll provide more details later. So then the second contribution is the region and dimensional ranking partitioning methods to enable natural parallelism. Then the third contribution is on the dimension reduction through specification guided ranking heuristics. So the idea here, we call our approach IntelliFeature. So the idea here is that this IntelliFeature is this IntelliFeature heuristic ranks the dimensions contributions to the output classification, and it gives priority to those dimensions that matter the most to misclassify an input. So due to the time limit, I won't be able to expand fully on this part, but I encourage you to look at our, Formulas 19 paper for details on this work, on this part of the work. Then in today's talk, I'll talk about our verification framework that basically, that integrates together all these techniques for augmenting existing verification algorithms with, basically with optimization in, in the first two fields above here. Okay, so that's this. So let me start by describing our refutation-based abstraction. So the idea is that we treat an input of a network as one region, or we divide the input into subregions, and we map each region of the input to a finite set of representative points. So this is what we mean by abstraction. So we use these, set of representative points to, to represent a given region. Then we, our work makes use of the adversarial example generation algorithms to first generate, try to generate adversarial examples. So the idea behind this is that, to say, a network or even a region is locally robust, it must not include any adversarial examples. So our thought is that, if we can generate an adversarial example from a region, then that region is not or cannot be, safe. So that's our, idea. So then basically we, by doing this, we can, reduce the cost to a more expensive verification technique. So for the refutation-based abstraction, we tried 3 strategies. The first one is the central point strategy. So basically, we just calculate the center of each region and then abstract that region or represent region using that center point, or several center points. Then the second one is when we have a region, we just randomly choose a set of points to represent that region. And the third one is the randomized fast gradient Sine method, or RFGSM. So I will expand on this third point in this talk, because this is our major contribution, and this technique also, this abstraction technique also showed the best performance when we evaluated on several examples. Okay, so. So before I introduce the randomized fast gradient Sine method, let's look at the fast gradient Sine method itself. So for this method, here is this I guess this equation of that describes this FGSM method. FGSM is a single-step adversarial example generation algorithm. So let me just give some detailed explanation of the symbols in here. So basically, on the left-hand side, we need to generate this perturbed input, which we call X with the ADV, or it's the adversarial input. Sorry, that's what we have, or that's what we try to generate on the left-hand side of the equation. On the right-hand side shows how we do that. So we have first, if we probably look at inside here, we have the cost function J, that is a measure of error between the DNN's predict output value and what the value actually is. So so this J is actually, or this cost function is actually obtained during the training of a neural network. And J, this cost function is a function of theta, which represents the internal parameters of the network, and X is the input of this it's an input of the neural network, and y is the ground truth of the desirable class for input x. So then basically we take the gradient of the cost function with respect to our input x. And what we obtain is basically, a kind of decision made by the gradient about the fastest way of modifying our input x toward an output class change, such that when we take the sign of this gradient and multiply by the small parameter sigma, we can add this small quantity to the input x such that we obtain this adversarial input where it can cause the output to misclassify. So this, as you see, this adversarial input x is just a slight perturbation of the input x here. So the issue, this FGSM, was presented by Ian Goodfellow et al. A few years ago. And the problem we observe is that there's relatively low variance in generating the output adversarial examples with this input. So that's why in our work, we modified this FGSM to introduce some randomization. We call randomized FGSM, or so in this case, we modify the expression like this. We introduce this sparse binary mask M. It basically can select dimensions of the input X to be manipulated by FGSM, or random values in R, which can be either -1 or 1. So if you look at the function of M, it is actually masking the dimensions of the original FGSM, and it allows those dimensions to be randomly selected as -1 or 1 to be added to the original input X. So, after multiplying with some smaller, a small parameter sigma here. So in this way, we actually can increase the output variance with M coupled with R. So, so our goal is that we want to construct a sparse a matrix M to maximize the output variance and the success rate in generating adversarial examples. So we propose this gradient-based dimension ranking heuristic to set or to determine this sparse matrix M. So basically, this heuristic will actually vary dimensions, or the result of this M will vary the dimensions contributing the most to the output classification with FGSM, and it will randomly vary dimensions deemed to be less critical. And we use, as later in the result, we'll use this balance factor to measure, the ratio between the dimensions manipulated using FGSM to those randomly, varied. So in this case, our results actually, later I'll show the results. So the results actually show that our RFGSM generates adversarial examples with improved representation of the regions they abstract, because they are not limited to merely the direction defined by the gradient, as is the case for FGSM. So here I use this, very simple illustrative example to show the the high level idea or the difference in the high level idea between the two techniques. On the left, you see this is the Flask gradient Sine method. So say, if our input consists only two dimensions, X and Y, the FGSM will, find the gradient as is indicated, by the, this left pointing arrow or northwest pointing arrow on the left of the figure. It will generate the adversarial examples along this direction. On the contrast, if you look at the right-hand side figure with our RFGSM, we still make sure that the important dimension is, it's going to be manipulated by FGSM. So in this case, we assume that the X dimension is the important one. So that's why we only generate the adversarial examples on the right-hand side or the right half of this graph, because we need to follow the the left direction of X. But on the other dimension Y, say Y is not the critical one. In this case, we allow it to vary. So basically, we are able to cover a larger size of region when we find these adversarial examples. So to test our idea, we chose three data sets. They're all, for image classification techniques. The first one is this MNIST data. It consists of, handwritten digits of 0 to 9. There are 10 classes, and it includes over 60,000 grayscale images. The second data set we chose to benchmark our method is this CFAR10. So it's a label subset of the 80 million tiny images data set. So I think this little frog on the right-hand side, top right, that's from the CFAR10 image set. And it also includes 10 classes with over 60,000 RGB color images, or colored images. Then the third data set is the GTSRB. This is the German traffic sign recognition benchmark. So it has 43 traffic sign classes with over 50,000 RGB images. So let's look at how our RFGSM compared to the FGSM. So on this figure, we show the plot of basically the three heuristics we used. The random is just for it's just some base method that we used as a reference. Then intelligent feature is this heuristic I briefly mentioned before about ranking important or favoring important dimensions to manipulate to cause a class change. And then the gradient based is actually what we have or is our most recent heuristic, where we based on the gradient of the cost function, we choose the most important dimensions. So I should mention that. Let me just briefly go back. So the gradient based heuristic is what we use to determine the the set M. So that's this. So as you can see, so on the so let me just talk about the the axes. So on the x-axis we have the balance factor. So the the balance factor decreases from left to right. The higher the balance factor, the more FGSM, RFGSM, becomes. So basically, if we look at the leftmost point, this is pure FGSM without any randomization. But if we look at the rightmost point or rightmost side, then it's close to entirely random selection of dimensions to manipulate. So you see that the gradient based maintains, the highest success rate in generating, the adversarial examples. so it's actually the, so as we vary the, the balance, this balance factor, we can actually we show that the gradient base is the most stable, among the three. So this is the result for the MNIST data set. Now for CFAR10, we observe even better, result for the gradient based. It's, it maintains very, very, success or very high success rate for generating adversarial examples until we're, we reduce the balance factor to 0.3 or even lower. And also you see that, the other two heuristics have produced very, success or a lot of success in generating adversarial examples. And observation we had here about the CFAR10 is that it seems that it's very easy to generate adversarial examples. As you see, like when the balance factor is higher than 0.7, we have almost 100%. We can always generate adversarial examples. So then the results on GTSRB also show, the advantage of the gradient-based approach in maintaining the success, the highest success in generating adversarial examples. Okay, well, as a second point of contribution, we have this region dimension ranking partition method. So here, our idea is that it's hard to, or, the neural network has a very high, input dimension. So we want to partition the dimension such that we can, basically apply the divide and conquer approach to, to do adversarial examples, then followed by, verification. So basically the question is that, which dimensions should we, subdivide first, and how aggressive should we, partition the regions of the input so that, it facilitates efficient verification. So we actually evaluated several strategies on different ways of partitioning the, the region dimensions. And I should mention that those evaluations you will see on the next slide are all based on the best abstraction strategy we found previously, which is this RFGSM and the gradient-based RFGSM. So here we actually tried these four different partitioning strategies. Random is, again, this is like a base case where we just randomly partition, our input regions and dimensions. Then for the gradient base, this is where we, again, use the gradient of the cost function to decide which dimension to partition first. The intelligent feature is the one that I mentioned before, and the largest first here is where, we just, partition the largest dimension first, so that we get almost equal size regions, almost throughout the entire, process. So we find that for the first, you see that largest first provides the highest number across the three data sets in terms of the number of generated adversarial examples. And this obviously is the, the winning strategy, that we are interested in. So this is the partitioning strategy. Now, so far we have talked about basically, our abstraction strategy and dimension partitioning strategies, and the optimal combination seems to be this. It's the RFGSM with, gradient based for abstraction, and the largest first dimension ranking for partitioning. So So our idea is that let's put these strategies together to form a verification framework. So we first want to employ the gradient-based RFGSM abstraction to efficiently refute the property, basically the property of local robustness, if whenever possible, before we actually apply verification. So that's why we call our approach refutation-based, because we want to find adversarial examples because they are easy and fast to do before we actually perform the formal verification. Then along the way, we need, we apply efficient partition strategies, basically the largest first region partitioning strategy, so that we can, partition, large regions into smaller ones incrementally, and then this actually allows abstraction and verification in parallel as well. So the verification strategy, basically after we have exhausted, the adversarial examples, the verification still needs to happen because it needs to give this formal guarantee of local robustness. So the verification strategy should scale in algorithmic complexity directly proportional to the size of the region. So let me just give you a walkthrough of the verification framework we have developed. So basically, the framework can optimize verification strategies with these 3 points that I mentioned on the previous slide. Now, what does the framework report, or what does it provide? It provides a set of covering adversarial inputs. So basically, it provides these adversarial examples or inputs, adversarial inputs that cause the misclassification, and it provides a coverage metric on on how much or in proportion how much region they cover in the input space. Secondly, it provides a set of safe regions. So that when for these safe regions, basically we can show that they are indeed robust to local adversarial perturbations. The third element or component of the output is a set of unsafe regions with counterexamples or adversarial examples. So this is actually useful for retraining the neural network to increase the robustness. Then lastly, it provides this incremental report generated for early termination. So basically our framework is can have anytime termination, even if you say just want to run it for 5 minutes, you can terminate and it will provide the incremental report for that. So on the right-hand side, we show, this flow chart or the, roughly the flow of our verification framework. So I will describe some of these major parts on the next few slides. Now we start with, this initial region, which we put it into the region, P, which is the unverified region set. Then we go into this while loop. This is where we start to, this is where we start to partition our region. So, so basically, if P is not empty, then we actually will, we'll come to here. Basically, we'll start by taking small region R from P, where we check R to see if it has any, or if it contains any adversarial examples. So we keep doing this until P is empty. So that's this major loop, and the anytime termination is indicated here. So at any time we can just stop and give us termination signal. Then the framework will generate the report for that. So here we use U to represent the set of verified unsafe regions with their associated counterexample. So that's why each element of U includes this small region R and this alpha, which is the counterexample. So basically here, if we're in this part, what happens is that we're gonna take out this small region containing a known counterexample from U, and then we'll try to partition the rest of U, because U is the it might be a too large of a region to be considered as unsafe. In a way, we're actually refining our unsafe region to make it more precise. It might be the case that after we remove the small region R with alpha, the rest of U is safe now. It was not safe because it contained this small region here. So that's what happens here in this part of the graph. So we use the set S to represent the verified safe region, and E as a adversarial example set, which we'll use for retraining. So in terms of once we're in this part on the on verification, basically we have these three sets to deal with: unknowns, unsafe, and safe, right? For safe set, we don't need to do anything else, but for unknown and unsafe, we need to keep partitioning those. So this is the the step for the safe set. It's just saying that let's add this small region R into the set of a set of safe sets. So let's look at the unsafe set. So basically, when we claim that a region is unsafe, as I mentioned, we can keep partitioning this region into n smaller regions, R1 to Rn, this lowercase r, and we try to find adversarial examples on or within each region. And if we're able to do so, we remove this region containing alpha, we call that Rx, but add the rest to the set of unverified regions. And then we can repeat this process with dealing with unverified regions. For the unsafe region, we can just add it to U and extract the adversarial example alpha. So then for the unknown set, what happens is that we're going to partition. We do the same thing. We partition into n smaller regions, and then for each such region, we perform abstraction to use points in each region. And then we check for each such point if there's if it causes misclassification or not. So that's where we iterate through this loop until we can determine all of these. Okay, so then evaluating our verification framework on these three data sets, we get these results here. So again, we choose three different strategies: random, gradient based, and intelli-feature. We see we actually show the size of the verified region. The size of unknown region and the size of unsafe region and the adversarial examples generated. So you see that for MNIST data, the gradient based is giving us the most counter examples generated, and it I think so it actually performs, or this strategy based or gradient based, it performs the best. So it gives a best performance across these three categories in terms of adversarial examples generated. Then for these other two heuristics, we see that for CFAR 10, for the CFAR 10 for evaluations on the CFAR 10, we have large number of P, or the size of P is much larger for the random and intelli-feature than the gradient based. But we want P to be smaller because it's, if you recall, P is the unverified region set. So the smaller the P is, basically the the less work is left to be done for the verification. So so this is what's our framework, or this is the evaluation results of our framework on these 3 data sets. Now, to conclude this work, basically we have presented this RFGSM as a refutation-based abstraction strategy, and RFGSM improves the efficiency of verification. The gradient-based dimension ranking increases the output variance while maintaining the success rate, as we saw on the last slide. And in our framework, we actually leverage the parallelism, to give us near linear speed up. We actually generate these results with 10 threads, to run the verification work, because each thread can just, work on one region itself. And then the next one is the partitioning strategy. So partitioning enables parallelism and produces a covering set of adversarial examples. And we also briefly, we recently evaluated the effect of retraining using these adversarial examples generated by our framework. We actually saw, a huge increase in the robustness after retraining using the adversarial examples from our framework. And our framework usually generates the adversarial examples really fast. Usually it happens within the first few seconds after it starts. And using those adversarial examples, we can already improve the robustness of a neural network by retraining significantly. So as for the future work, you probably saw that I didn't talk a lot about our verification engine. This is because our verification engine is still in the development phase, or it's still in the phase of being improved. Currently, we actually use a naive method for doing verification. So we need to improve the strategies that can scale with the region size. And also, because our framework has been designed, with the consideration of potentially including, these other, techniques for abstraction, partitioning, and verification, we're thinking about, the possibility of integrating other DNN verification techniques into our framework, so that it can work with, our RFGSM and partitioning strategies. So then also we plan to explore more efficient and reliable, refutation-based abstraction strategies, and also other abstraction methods that preserve the safety properties. Okay. So I provided here the 2 links for our work. The first one is the verification framework I mentioned. The second one is this heuristic feature guide heuristic for ranking dimensions. And I'm ready to take any questions you might have. Thank you.
Yeah, I had a question on the FGSM equations that you were showing in one of your earlier slides.
Yeah.
So
sure. Let me go to that. Yeah.
Sure. Yeah. So I think you're trying to basically pull the input towards a different class label, which is not the correct one. But how do you know which one to pull it towards? Like, do you take the closest class label?
No, FGSM doesn't give us that choice, so it's not targeted. So FGSM's its only goal is to cause the network to classify into a wrong class. It doesn't know which wrong class it's going to classify it into. Does that make sense?
Okay, so you're adding noise and kind of
Yeah.
hoping that there will be a different label which is in the neighborhood of the correct label.
That's right. Yes.
Okay,
yes.
nice.
Yeah.
Yeah, that's cool.
So related to that, when you've generated some adversarial examples and you know that it causes a misclassification, you said that you then retrain the network. How does that look? Does someone have to go in and label them manually, or do you figure out which label it went to and know it's at least not that label?
Yeah, we have to manually label, or well, so yes, I think we have to still, to tell the neural network which one is the correct label. Yeah. But so our recent, experiments show that, even with, adversarial examples generated on a very simple network, for example, we tried actually, a network with 3 hidden layers, feed-forward networks with just 10 neurons on each one. We were able to generate a lot of adversarial examples, and then we can use those to train a much complex, neural network with, convolutional layers and much more neurons on each layer. And we saw that robustness on the training result is actually pretty good. It's close, I think it's close 100%. Even for a more complex network without any training, without any prior vanilla training at all, we can just train the complex neural network with adversarial examples generated from our framework on a simple one that actually achieve quite significant improvement in terms of the robustness. Yeah.
I have a clarifying question.
Yeah.
So when you perturb an image, is it, are you like locally perturbing the pixels? Is that the model of error?
Right, yes, exactly. That's done by this. So this part. So we take the sine of the gradient of the cost function, multiply that to a very small parameter, and then add that to our original input. So yes, that's exactly what happens. Yeah.
But is this group of pixels local in the XY? Let's say it's a 2-dimensional image.
Yeah.
Okay. So when you say it's verified, you mean against this perturbation model? Like if there was a picture which to humans look very similar, but is because there's noise added to different regions that you won't catch with the verification.
Well, unless we go and verify that particular region.
I guess
that's why it's called local robustness. Yes.
So
yes.
if the neural network makes a mistake because you need to have more than one local region perturbed, then you can say that it's verified against this model, but you can still have a case like that.
Right.
Thanks.
Can I follow up on that? So how closely does that definition of local robustness map to the safety failures that you described at the beginning?
Okay. Is it this one? The local robustness, right? So basically we're saying that this region here, this eta, if it's locally robust, we should never be able to find an adversarial example or any points contained within this region which causes the output to misclassify.
Yeah, and so then like with the Uber example, is that local? That's what I don't know.
That I have no information, unfortunately. So, but according to an article I read on the that article I read, it's actually due to the perception module, and it actually misclassified the the pedestrian with a bicycle as an unknown object first, and then it thought it was another vehicle. And then in the end, it correctly classified it as a pedestrian, but it was too late for the prediction module to apply the brake of the car. So that's how the accident happened. But whether that was due to misclassification or that was due to local robustness issue or not, the article didn't really give any more detail on that. But I think I should look into to see if I can find more details about this. But there have been experiments people tried, when they they put like a band-aid on a stop sign, and then all of a sudden the neural network thinks it's something else instead of a stop sign. So that could be or we could formulate that kind of problem into this local robustness problem, because it's just small perturbation on the original image that basically fools the neural network.
So why fast gradient sine method? I've got to ask.
It's the most efficient method for adversarial example generation we know of. So that's why we chose that. There we look at some other alternatives, but this one seemed to be the fastest. And that's what we want. We want to quickly find those adversarial examples from our framework first, right? So that just fit our purpose when we started this work.
Yeah, fast gradient sine method is the fastest, and it's also the lowest quality. But what you said makes a lot of sense. It's a totally justifiable reason. Do you have like benchmarks or something? Did you have some performance goal you were trying to hit that drove that concern of wanting the best performing rather than the best quality adversarial example?
That's a good question. But actually, we didn't consider quality versus speed. We probably looked just at the speed when we started this work.
I'm actually now curious.
We also looked at the JSMA. Sorry, go ahead.
No, I was just curious, when you meant quality, what do you mean by quality of an adversarial example?
Me?
Well, in general, I guess it's a question for just a question. Is it because I didn't realize there was a quality of an adversarial example? It's a counterexample. Yeah.
Yeah, I the simplest definition would be the magnitude of the perturbation being smaller, right?
Yeah.
Well, an alternative definition would be maximizing that loss. Like, what is the maximal value of that loss?
Yes. Usually in a classification problem, you're interested when it goes from pedestrian to bicycle, right? There is a decision threshold. But yeah, that you find that anyway. Go on.
Sorry, I was curious. Do you have suggestions of other techniques to look? I mean, we look at JSMA as well. That's a more targeted, adversarial example generation technique. But that seems to be slower according to our understanding than FGSM.
Yeah, I mean, everything else is going to be slower. Projected gradient descent is the whole family of nonlinear adversarial example finding, right? The nice thing about FGSM is that you only have to do one gradient computation. The downside is that you're constrained to the local linearity of the decision surface. So sometimes, that surface is wildly unstable. That's kind of why there are adversarial examples. So, if you don't do a multi-step thing, sometimes you miss a cliff that's just a little bit away because the local linear point's somewhere else. But to go a different direction, and maybe I just missed this, sorry, but when did you decide to stop generating adversarial examples within a region?
So the framework doesn't stop it. So the way it works, it partitions the inputs and tries to generate as many adversarial examples as it can. and once it stops finding adversarial examples, it will, invoke the verification engine on the partitioned, hopefully very small regions to make sure to check basically point by point to see if, any adversarial examples skipped the generation part. So yeah, we don't, I guess when it completes, then it will stop. But according to our evaluation, currently it takes, some time to finish. So that's why we implemented this anytime stop mechanism. We can always stop by killing the framework and then just obtain hopefully enough adversarial examples to retrain. So that's why I said we still need to improve the verification engine side because of, the expensive operations.
Gotcha. And as far as classifying a new adversarial example, I assume it's like a distance threshold, right? If all the ones that you're finding are close to ones you've already found, that's
right.
Okay.
Yeah.
Thank you.
Okay, Dr. Zhang, I guess if there are no more questions, we'll go ahead and stop it here. And then if you would like contact information for anybody who has had questions or whatever, and vice versa, everybody just let me know.
Sure, thank you. Yes, and also feel free to share my contact information. I welcome feedback and ideas like the questions I got today. Yeah, they are really nice questions. I really appreciate the your interest. Yeah, I always welcome feedback and ideas for further improvements.
Of course.
Yeah. Do you mind if I mention briefly about our other, my other research work in case people are interested?
Yeah,
just very briefly.
everybody should feel free to drop off if you have other commitments, but go ahead and take a few minutes if you'd like, Dr. Zhang.
Sure. Okay. So, in addition to the, verification work we do here, we also, work on probabilistic verification of network on chip, systems, and also synthetic biology models. So basically, we apply, probabilistic verification, but with state-space truncation because of the size of the states we have to deal with. Also, we work on this. I guess, well, the verification of sorry, just one sec. Oh yeah, so we also have some research on using symbolic techniques to to do verification again on a complex routing algorithm for on-chip network. So we have been able to scale that verification a lot. We're applying this iterative unbounded model checking techniques to help us to find basically live log issues where a network packet can trap on a network without ever reaching the destination. So we have been really successful in that, and we are thinking about probably incorporating some of these unbounded model checking techniques into, say, the neural network verification. Okay, so that's, I think, all I want to say, but I'm happy to provide more details if any of these areas is of interest to you. And I'm happy to also talk to anyone, set up a one-on-one meeting to give you more details of our research work. I'm actively looking for collaboration opportunities as well. Okay, thanks.
Okay, that's excellent. All right, thank you, Dr. Zhang.